Well, hello, we're live. Thank you for joining us on Relax Radio for Happy Maths Hour. Please, whatever platform you're on, please feel free to share it. Don't feel free, just do it. Share it with your friends. This is Happy Maths Hour. Today we're going to talk about triangle numbers, but it's all about number patterns. It's how to engage your learners to be fascinated by mathematics, and that's what we're here to do. We want to help your learners gain fascination with mathematics. After the break, our lovely Toni is going to take us through how to make this happen.
It's time for a show on Relax Radio. It talks about me and you. It's time for a show on Relax Radio. It talks about me and you. So listen to us here 24 hours and let the happiness come to you on Relax Radio. Tune in to Relax Radio. Relax Radio.
Oh, I'm going to take that off first. Welcome, Toni. Thank you.
Hello.
Thank you again. I mean, I shouldn't say thank you. Welcome. I don't know, because we're co-hosts here. So how does one welcome everybody to the show with myself and Toni? And today, as I say, we're going to discover more about triangle numbers, that it's all about patterns. It's about gaining fascination. It's about how you can become fascinated and help your young learners become fascinated in most intriguing things in mathematics. Go ahead, Toni. Tell me when you want me to add.
I want to know if everybody can see my my screen. Can you see it?
No, not yet. That's what I was asking. I was just introducing us, and here we go. Now everyone can see the screen with my lovely scruffy hair. We've got to change that picture, Toni.
Okay, so here we go. We're going to, as Caroline said, today we're going to talk about triangle numbers, and there's lots of patterns here. There's patterns of shapes, we call those perhaps geometrical patterns, and there's patterns of numbers. So, well, Caroline, what do you notice about these patterns?
Let me see. Well, I can see why they're called triangle numbers. I see that, well, there's the dot. That's just one dot. So that one I'm not sure about. But the others are very clearly triangle numbers. And I can see that if they're static, we're not moving them. Each one has got well, let me do it the same way around and that way around. Each one has a diagonal line added. But also, something else that I feel like it's as though it could be a column that's added, or a row, a column to the left, or a row at the bottom has been added. But they're no longer static, but they could be built up doing it that way as well. I see that.
Caroline, you mentioned number one. Well, quite often in mathematics, something arises which is a simple case of a general pattern, and one is the first triangle number. You're not seeing, as it were, a triangle of dots there, but it is consistent with what you've just described. The way the pattern is formed by putting an extra row or column or diagonal, whichever way you like to think about it, the pattern is growing, and it's starting with one. And so one is a quite simple triangle, but it is a special case. So if you shrink the triangle numbers, if you think of shrinking them down by taking off a row, then you get back to one.
Right. Okay. So one is valid to have in that sequence.
Indeed.
So that's nice. That's comforting to know. So what else have we got? I can see, yes, I see your numbers. I'm looking at this. So T1 to T6, I take that to be a triangle 1 is a single dot. Triangle 2 is 3 dots. And then I've got the numbers below where we've got 1, 1 plus 2, 1 plus 2 plus 3. Well, I can see that very clearly. That is how many diagonal dots there are. So in the diagonal, wait a minute, let's follow the same that way. One, there's just that's Tanya. And 1 plus 2, there's a dot, and then there's a diagonal with 2, and it just goes
Caroline,
on.
can I just say, I agree with what you're saying. Of course it's right, but it is easier if you start from the top and go down. So if you think of, oh yes, I wanted to say also that these, we want to give them a name. So we're calling them T1 for the first one, T2 for the second one, T3 for the third one, and so on. The 100th one is called T100, and that thing, we write the number down as what we call a subscript. So the next one isn't shown.
Hold on, Toni. I'm not ready to go there. You said something, and I was adding the diagonals on, but now you said it's easier if you go down. So you're adding a row on. You're saying it's easier.
I think that's easier.
Upwards. So it's going upwards, and you'll keep adding a row on at the bottom.
No, start at the top and go 1 plus 2, 1 plus 2 plus 3, and then for T4 it's 1 plus 2 plus 3 plus 4. Look at the rows and just go down. And you'll find.
So for each triangle,
you can do anything, Caroline. It's fine to do what you were doing.
Because I've always looked at the because we've always had them in the past. We've had them laying on the hypotenuse on the longest edge. So you've turned them around on me. So you can do it just as that's what I meant about the rows and the columns anyway, that you can quite happily add a row at the bottom of if it sitting this way. You can do it whichever way it's sitting.
That's a nice thing about it. I mean, there's different ways of looking at it, different ways of visualizing the triangle, if you like. But my point was that what you were doing was, what you were saying was absolutely right. But it is easier, whichever way round the triangle is, to start at the top and work your way down, because you've got 1 at the top, then underneath it you've got 2, then underneath it you've got 3. And when we come to T6, it's 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is why we
going down. Yeah, I can see it. Yeah. Mm-hmm. Okay.
Now, then there's a question, and this, you wouldn't really want to draw the dots for this, would you? For T100.
No, I don't think I want to draw the dots for T100. Thank you very much. No.
So let's approach this a different way. Let's try and do it an easier way. So this is a little bit of a diversion. This is about, this is about clever Carl. And the story is, it's about Gauss, who was a famous mathematician, but of course not famous when he was a child.
Was it? So his name was Carl Gauss, was it?
Yes, and he was Carl Friedrich Gauss. But he, as a small boy, his teacher gave the whole class to add 1 plus 2 plus 3 plus 4 up to 100, which is the question we just asked. And the teacher thought he'd given this question, the children would add these numbers, it would take them quite a long time, and the teacher could just sit back and relax, and it would be good practice in addition for the children. Well, the teacher got a surprise, because in about 2 minutes or less, Carl put his hand up and said, "Sir, I've done it." And his teacher was hardly could believe it. And so he asked him what answer he got, and the boy told him the answer, and then the teacher knew that it was right. And so this is what he had done. Can you see here? Adding the numbers 1 plus 2 plus 3 plus 4, and going on up to 99, and then adding 100, going from left to right, you can imagine that. And then what Carl imagined, which was extremely clever, was to flip them round and start, instead of starting at 1, to start at 100. And instead of counting up, to count down. So he counted 100 plus 99 plus 98 and so on. Well, he didn't add them. He just wrote them in that order. Yeah, he just wrote them in that order.
In the reverse order, he wrote them in the going 1 up to 100 going up, and then starting at 100 going down to 1. And it's got an insight. What an incredible insight that was.
So what do you see about that pattern?
Well, what I see is, and it makes total sense seeing it, is that 1 plus 100 is 101, 2 plus 99 is 101, 3 plus 98 is 101. It's just the thought of actually having done that, having reversed the numbers, if you do that with any number, presumably, you end up, if you add those two numbers together, you will always end up with the same number.
Yes, if yours, it actually works for other, these are called arithmetic sequences. It works for any of them, because if you take the same sequence and reverse it, and you go up with one, when you write the sequence down one way, and then you go down when you write the sequence the other way, the sum of the terms that you've put underneath each other, as it were, will always be the same.
Fantastic.
Isn't it lovely? Yes.
Absolutely.
And so what's this? This gives us the answer to the question we just asked. It gives us to the answer beautifully. So the T100.
So, okay. Go on. Sorry, you say that. Yeah.
Well, no, Caroline, you can talk about it.
Well, no, it's just that I'm looking at it, and I have looked at this before, but I'm interpreting it again because I find it so beautiful. So it's happening 100 times because we've got numbers 1 to 100. So we've got 100 events here. And if we add each column, we always get 101. So we've got 100 times 101. We've got 100 events of two numbers being added together to make 101. But we're actually only wanting to add up 1 to 100 with all the numbers in between. So it's actually half, because it's 100 times 101 is the numbers added together, like the two sets of it added together. So if we only want one half of it, we just halve it, and hey presto, without doing anything complicated at all, we get the answer. Because especially since because it's 100 numbers, that helps us. 100 times 101 is super easy to work out. That's 10,100, and then half that, bingo, 5,050. It's I love it. I really love it.
Well, when he grew up, he became this young man, Carl Friedrich Gauss, as you can see on the stamp. He was a famous mathematician when he was still quite young. And there is a picture of him, not as a boy on this stamp, but as a young man. And here's a picture of him on a banknote as quite an old man. This was Carl Friedrich Gauss, born in 1777, died in 1855. And he was what people have described as a polymath. That actually didn't have anything to do with mathematics. It was more a description, math being used there in the sense of what you know and understand. In his time, in the late 18th century and the early 19th century, a scholar could know more or less all that was worth knowing. Well, not so much all that was worth knowing as what was known was so limited that one person could actually learn it all in his lifetime or her lifetime. Nowadays, there's so much out there that's been discovered since Gauss that it would be absolutely impossible. And what's even worse in the sense is that there are new discoveries being made every day, faster than anybody could, in mathematics even, if you just stick to one subject, faster than anybody could possibly study them and learn them. So yes, there's been an explosion of knowledge, really.
And yeah, but having said that, Gauss was part of the explosion, because he didn't just learn everything there was to know, he developed it, he made new discoveries, and this is beautiful. Now, if people are saying to themselves, Gauss, that sounds familiar, I've heard of Gaussian distribution, would that be?
Oh yes, I mean,
Gauss?
he worked in very, very many different branches of mathematics, and he actually, as you so rightly said, Caroline, he laid the foundations for further work in all sorts of fields of mathematics. So you're right, he was part of that explosion, because he had so many good ideas that people later were able to expand on. And this was one of his ideas. It's called the Eureka theorem. And
let's put that one on. Go on.
And what his theorem was that every number, whole number we're talking about, integer, can be written as the sum of 1, 2, or 3 triangular numbers. Right? So you don't need 4, you can do it. Of course, the triangle numbers themselves are just one triangle number. And then there are some numbers that can be written as 2 triangle numbers, and all the rest can be written as 3 triangle numbers. Isn't that beautiful?
Yeah, and he did say Eureka. This is in his notes. You were telling me the story about that. The little block in red was actually discovered in his notes.
Yes, well, that's like Archimedes said Eureka. He's supposed to have jumped out of his bath and run down the street. He was so excited. But no, this is Gauss. Nothing to do with bath water or anything. His triangular numbers. Now, yes, it's just about coming up to time for another jingle.
Okay, I've got to say that the triangle numbers is I don't know if, okay, I need to repeat that before we do the jingle, that every triangle number can be created by adding 1 or more of the first 3 triangle numbers. That's it. Everyone can be created.
Any 3?
Any three.
Yeah.
Up to, because it can be 1, it can be 2, or it can be 3, and every triangle number can be made of any 3 up to 3. It's incredible. Okay, right. Here comes the jingle, and after the break, we're going to find another way of doing this. So you can draw lots of dots and different triangles. We're going to investigate another way of doing this. So she says that she's looking for the jingle. Here we go. And in English, we're good. Whoops.
It's time for a show on Relax Radio. It talks about me and you. It's time for a show on Relax Radio.
Right, I don't know what happened there. We're just going to proceed. We'll do it properly next time. So it's time we cut that short.
Another picture. What do you notice in this picture?
Well, I see 2 number triangles, but they're put together. They're not put together the way I'd expect them to be put together, because normally when I split, I can see a rectangle, but normally when I split it in half, I literally go from one vertex to another. So I'm literally splitting in half. This is 2 halves, but they're offset. So I've
they're actually the same triangle number, and it's rotated, and we've shown one in green and one in purple, so we can see that it's 2 triangle numbers. So what is the triangle number that is pictured there?
So that is 1, 3, 6, 10. That's 15. That's the triangle number 15, but it's 2 times. So there are actually 30 dots there. There are 2 15 triangles. So it's 2 times that amount of dots. So there's 30 dots.
Well, it's T5, isn't it? Because it's 1 plus 2 plus 3 plus 4 plus 5.
We have a nomenclature. We have a way of referring to these triangle numbers. And yes, if I use it correctly, I can get to that really easily, because all I have to do is count one edge. So I can count 5 dots. So therefore, it's a T5.
That's
okay.
right.
That's
and
easy.
What you said, Caroline, what you said was right. You've got a rectangle, and there are 15 dots in the green triangle number, and there are 15 dots in the purple one, which makes 30 dots altogether. But if you see the rectangle is a 5 by 6 rectangle. So what that tells us, that 2 T5 triangle numbers make a rectangle, and as you told us, that was 2 T5 triangle numbers is 5 times 6 is 30 dots. So that gives us T5 equals 15. And it's written there. And that's what Caroline just talked about.
Now wait, you said T1000, what, to work out T1000. So to work out T1000, all we have to do is say 2 times T1000 equals 1000 times 1001, which equal to whatever that is, which is, I have to write down the ones so I don't get the wrong amount of ones. And then that's how you, that's it. That's how you know.
Isn't that lovely? Well, we were talking about
half of that. T1000 is half of that.
Well,
you
said
you asked about 1,000, Tony. Now you're giving us 100.
Well, we had 100 before.
Oh, we did. We had the 100 example. Yeah, I was answering the 1,000 question.
Well, yes, why not? You could do it for no, Caroline. Absolutely right. You can do it for any triangle number now, however big. Right.
So yeah, I did have something that came to me just then, and it's gone. Never mind. Some other time. I should have written it down.
No matter. The point is that if we have any triangle number, it is the position in the sequence is what defines it. So T5 is the 5th in the sequence. T100 is the 100th in the sequence. Tn, now we're creeping into algebra, Tn is the nth in the sequence. T1000 is the 1000th one.
So 2 times Tn equals n times n plus 1. And when people talk about BODMAS, it's really important. You don't, once you really understand how numbers work, you don't have to think about BODMAS. But if you're confused about where the numbers go, I'll shut up, Tony. The point is that it is n times n. I'm excited, Tony, because I'm working it out. I'm loving the fact that I'm actually working it out. 2 Tn equals n times n plus 1.
Isn't that lovely?
And then so Tn equals n times n plus 1 divided by 2. And then you simplify it a little bit.
Yes. So what you can say in words without any algebra is that if you want to find a triangle number, right, you take its place in the line, in the sequence, and that's the number that labels where it is, like T5 is in the 5th place, T100 is in the 100th place. And that place number times one more than that place number,
right,
and then divided by 2 gives you that triangle number.
And you can visualize that using the image above, using that rectangle, that you're only working out how many there are in half of that rectangle. And so it actually really helps you. You can visualize the rectangles, therefore you know it's the length times the width, but you only want half of it. So it's actually, you've got a visual aid for it as well.
Well, you've got a visual aid there, and you've also got a shorthand way of writing it down, and summing it up for all possible triangle numbers, not just T5 or T100, but all of them. And what I just said now was doing it in words without algebra. But algebra is just a lovely way of actually summarizing. So to summarize it algebraically, you say that the nth triangle number, Tn, is a half of n times n plus 1, or n times n plus 1 divided by 2. Isn't that nice?
That is lovely. And I've got some news for you, Tony. We have 3 people from MACA, my friends in Barcelona, from the Maths Museum of Catalunya, are watching us right now on YouTube.
Well, that's great, because actually you could do this in primary school. I know these friends. They're focusing.
From Little E's all the way up to the top level. This works for them. They're going to like. They're going to love you. They haven't been exposed to your work before, so this is great.
Well, we don't need the algebra in primary school, but it's what we call in primary school pre-algebra. And yes, this idea is simple enough to do with children in primary school, and then it's a very rich activity for secondary school. Now I have another pattern for you, Caroline. What do you notice about this picture?
Okay, now that's messing with my head, Toni. Ah, my eyes are going cross-eyed. You did not prepare me for this. My eyes are going cross-eyed. Hold on. One has got more. One more. That's one's a 2, 4, 6. One's a T6, and the other's a T7.
Caroline, what you said before when you wanted to put the two triangle numbers together was you wanted it somehow.
Oh yes, no, you haven't. They haven't been shifted. But
well, you're right about it being a T6 and a T7. So what we've got here is two consecutive
together to make a square. Rather than a rectangle.
Absolutely, isn't that pretty? Two consecutive triangle numbers. You can picturize it, you can visualize it with that picture, and they make a square. That's what you said.
Yeah, hold on, we've got something for Sergio. Sergio, were you here when we did the rectangle though? Two triangle numbers is always a square. Well, that's not what we found earlier. We were making rectangles, Sergio, not squares. Two triangles, two equal
consecutive. Triangles. Yes.
These are two. Yeah, this is it. Two consecutive triangle numbers make a square, but two triangle numbers that are the same. Can you go back? Thank you, Sergio. If you now look at that one, if they're the same triangle number, they don't make a square at all. You can't make that a square.
They make a rectangle.
They make a rectangle.
And we've just used that. Now we've moved on to something new. And we've said, but if we take not two triangle numbers that are the same, but two that are different, and in this case it's T6 and T7, they make a square, not a rectangle.
And the diagonal of the T7 is actually bisecting the 7 by 7 square.
Yes, isn't that nice?
And Sergio says that is what he wanted to say. Remember, English is not his first language, so it's yes. Thank you, Sergio. That's great.
And so now,
sorry, Toni. We've also got Michael Mumbo from EduTab Africa. Do you know Mike?
Fantastic.
Welcome, Mike. I'm just going to send you a message. Please do, Michael, on Facebook, send us a personal a PM. We'd love to connect with you and find out more about you, please. Go ahead, Toni.
Well, what I was going to say was, what you immediately spotted when you looked at this was this yellow triangle number is T6, and the blue one is T7. And when you add them up, you get a square. And that square has got how many dots in it? It's 7 times 7, which is 49. Isn't that pretty?
That is very, so T6 plus T7 is 7 times 7. So it's 6 plus 1 times 7. And of course it's 49. That makes a square. Yeah, this is new to me. Sergio, this is, by the way, new to, okay, now he's saying it's all right. Sergio's filling in the thing he didn't say earlier. So this is actually new to me. I don't remember seeing this before, and this is blowing my mind. I'm loving this. I'm wondering how I can do this with balloons.
Well, you see, every time you take two consecutive numbers, there's nothing special about the 6th one and the 7th one. I'm just going to leave this for our audience to play with themselves. But if you look at the list of triangle numbers as we've built it up, we've been talking about it, and you put two consecutive triangle numbers together, I'm going to ask you a question. I don't want you to answer it now, Caroline, because it's nearly time for the break. I want to ask everybody to think about this after this session, or think of it whenever you like, if you want to, and see whether you think it's always true. Because I really believe that we shouldn't be telling them all the answers, Caroline. We should be giving them things to think about.
So is this always true?
Yes, for any two, is it always true that for any two consecutive triangle numbers, and there's infinitely many of them, but if you take any one and the one after it, that they add together to make a square number? Or you can look at it the other way round. You can say, can any square number be split into two triangle numbers?
Can any square number be split into two consecutive triangle numbers? So it's always the connection between the square numbers and the triangle numbers. Okay, that's where I'm going with it. I'll shut up. Oh my goodness, I'm getting excited here, Toni. Is there a connection between square numbers and triangle numbers? Oh my goodness. And go on.
And does this connect with the Gauss's Eureka theorem? Because remember, that theorem which we just talked about when we were thinking about Gauss was that take any number at all. I mean, I don't mean any number, actually. I mean any whole number or counting number.
Yeah.
You can write it as the sum of one triangle number. And well, if it is a triangle number, it's only one, and that's it. If it's a square number, it'll be the sum of two triangle numbers. And, well, will it? That's what we seem to be thinking about with this particular picture. And then if it's not a triangle or a square number, Gauss's Eureka theorem says, well, anyway, you can write it as the sum of three triangle numbers. We haven't proved that. But
do we have to say integers? Is it
positive integers or counting numbers or natural numbers? They're all the same, really.
Okay. So they can. The question is, okay, can they be expressed that way? And okay, can all square numbers be made up of two triangle numbers? So we're thinking about that. We're going to have our break
in a minute, Caroline. Though, when we come back from the break, we're going to think about what we've been working on last week and the week before, and where triangle numbers came up then, and what's the connection. Because now we know more about triangle numbers, we can think back to our handshakes after the break.
So we had handshakes, we had mystic roses, so we had some very physical things happening. We were representing them with diagrams. We had mystic roses, which are absolutely beautiful. Again, lots of lovely lines making circles and things. And how on earth do they connect with this? After the break.
It's time for a show on Relax Radio. It talks about me and you. It's time for a show on Relax Radio. It talks about me and you. So listen to us, 24 hours, and let the happiness come to you on Relax Radio. Tune in to Relax Radio. Relax Radio.
Welcome back. We've got our next slide here. I'm just letting you know, Sergio Belmonte says it's wonderful. And he's come up with an actual algebraic formula, generic formula. So just to let you know, I'm not going to say it out loud for everybody, Sergio, because Toni wants people to think about it.
I want everybody to do it for themselves.
Yeah. So, but it's thank you for your participation. I'm loving this. I've got my Maca friends here. Oh, I'm so happy. Go on, Toni. I've got Toni and Maca all in one environment.
A couple of weeks ago, we talked about the handshakes problem, and this is simply the problem that if you have however many people you've got in the room and everybody must shake hands with everybody else, how many handshakes would that be? Now, with COVID and social distancing, we've replaced the handshake with a bow, the Japanese style bow, where you bow for, not like a performer does on the stage to the whole audience. In this particular case, it's the Japanese greeting where you must greet one-to-one. So it's a one-to-one greeting. So you don't hold hands, but you each bow to each other. So whether it's handshakes or bows, how many would there be? Now, as you see, this is a classroom in Tanzania. I took this picture. I was working with these children, and you see on the board there, it says handshakes, and then it says people, and where it says whatever, handshakes, it's a number of handshakes. So if there's only 2 people in the room, well, that's easy. It's only one handshake. And if there's 3 people in the room, the children had just worked out that if there were 3 people and everybody shook hands with everybody else, there would be 3 handshakes.
So it's two people, 1 handshake, 3 people, 3 handshakes. Okay, go ahead, because it's hard to read. I'm just reading it out.
But now these 4 girls at the front are working out. There's 4 of them, and they're working out how many handshakes. And the children in the class are watching and counting as they do the handshake. So everybody's participating, but it's the girls who are actually doing the handshakes. And they're trying to find out how many handshakes that would be. And, well, we talked about this quite a lot a couple of weeks ago. And remember, it could be vows. I was in Bagamoyo. It's a lovely place on the coast of Tanzania and just across the water from the island of Zanzibar. All very romantic. It's a wonderful place.
It's spectacular, yeah.
It's a wonderful place because, as you see in that classroom, there's a mixture of Christians and Muslims all living very harmoniously together, as they have done for a couple of centuries. And there's a lovely story there, but we told that last time. Okay.
We have one answer. We've got someone that's come up. David has come up with an answer.
But Mecca. Just
I know we're not.
Don't reveal it. Well done. Well done. Don't reveal it.
But there's something I want to just say. If anyone, I've been talking about my friends from Mecca. They're in Barcelona. It's the Maths Museum de Luna. I've put the URL at the bottom there, so you can go to that URL now. Apart from having some very interesting activities that they do, they're hands-on. You can actually buy their resources. They've got a lot of things for sale that they'll ship anywhere in the world, and they are really good for learning, getting your learners to get hands-on understanding of mathematics. Just wanted to say that.
I think that science museums and maths museums are absolutely wonderful, and there are many of them around the world. And when you mentioned your friends in Barcelona, I was a bit confused because I thought you were talking about education.
No, this is Mecca. Yeah, this is.
No, but they know about education, and that's where we've been working with teachers of primary school children. That's why I mentioned primary.
When she talks about Sergio, this is the Sergio, the one that's watching is the Sergio she talks about.
Right. Okay. So now, what we were making with the children, and it's a bit tidier here than you see it on the blackboard in that classroom in Africa. Here, we made with the children, and they, after they had done that in groups of 4, they all of the children made up groups of 5 and tried it out and worked out how many handshakes for groups of 5 and then 6. And these were the answers that they got. And if you think about what we were doing a few minutes ago, when we're talking about triangle numbers, I'm sure you'll recognize that those are the triangle numbers, 1, 3, 6, 10, 15, 21. But this time we've chosen to do a rather obvious thing, to say, well, we need to really include 1 now, not triangle number 1, but the number of people. So if there's only 1 person in the room, there's nobody else for that person to shake hands with. So now we're starting at the triangle number 0. And that's even more of a special case, Caroline. You see, you thought that 1 was rather a peculiar triangle number. And now, if you see that if you keep going back, so from 21 to 15, you take off 6. And then from 15 to 10, you take off 5. And then from 10 to 6, you take off 4. And then you take off 3. And then you take off 2. And then you take off 1. You go back to 0. So you see, the 0, on, as I called it, 0, is in the same pattern, isn't it? So it is a special triangle number. A bit special because you couldn't draw well, you can imagine no dots or one dot and being a sort of shrunken triangle, but there it is. So
yes, no, that is very intriguing. That's one of those things that a mathematician has to do, is to visualize things like that, or to go where it's nothing, and there's nothing there, or it's infinity. And that's one of the beauties of doing the work in your head. There's a mathematician behind Toni right now, a very, very easy mathematician. I'm just putting a link to the handshakes activity. Now, I've only put the link in the description to the triangles. I'll add on YouTube, I'll add all these other ones so that people can just click. So if you watch this on YouTube, you'll find links to all three activities. We've got so far handshakes, we've got the triangle numbers. So what was the other one, Toni? Sorry, are you ready? No, I'll wait. I'm not.
Well, after the break, we'll come to Mystic Rose. But let's think again about the triangle numbers. Now, Caroline was saying earlier that she wanted to see the triangles look like that, which we'd looked at before, that like the red balls there. But in fact, when we looked at them earlier, they were sort of on their edge. They weren't like these balls. They were, they were drawn a little bit differently. And in fact, these are equilateral triangles, whereas the triangles that we saw earlier were right-angled triangles. But
right.
The whole point is they are the same pattern, aren't they?
Okay, so it still works. Okay, go ahead.
So T4 is 1 + 2 + 3 + 4.
Mm-hmm.
And you're being asked here, what is T5? Because there's a question mark there and the picture isn't drawn for you. And well, but all you have to do is to think of the pattern. And it's 1 + 2 + 3 + 4 + 5. And it's a bigger equilateral triangle that stands a bit higher, with a row of 5 along the bottom.
Along the bottom, so it bumps up. Sergio's come up with what has he said? He said, how about the number of diagonals of a given regular polygon? So how many, something to make a connection with the number of diagonals of a given regular polygon, diagonals, okay. And then the other one is, perhaps there's something to investigate there that might trigger some curiosity. I certainly do not know the answer to that, Sergio. And in addition of the size is exactly the number of handshakes.
I think what he's saying there, Caroline, is that what we were saying anyway, that the number of handshakes is the triangle number. So but you what you have there is don't be confused, anybody, by this, but we're now in the pattern of red balls, we're starting at 1. In the number of handshakes, we're starting at 0.
Yes, because there's 2 people to make 1 handshake, whereas with the balls, 1 ball is 1 triangle. Well, is 1 is 1, whereas with 2 people makes 1 handshake. So 1 person, there are no hands, because you can shake your hand, but it doesn't count.
But to go back to what your friend was saying about diagonals of a regular polygon, I mean, there's lovely questions here, and that's a lovely question, and we'll leave that for people to think about, because we're coming up to the break, aren't we? We
are, and I'm just going to respond to Sergio, because we've got involvement here, Toni. When we've got involvement, we want to. So he's now given us the answer. Basically, yes, he clarified what he was saying, and yes, what you said, Sergio, is the conclusion. We're not going to reveal it because we're going to look at that after the break. Thank you. And oh my goodness, I was so busy watching the messages, I didn't get the video ready. See you after the break with the number pattern. So basically connections. We're making connections in maths, which is where all the excitement happens.
It's time for a show on Relax Radio. It talks about me and you. It's time for a show on Relax Radio. It talks about me and you. So listen to us here 24 hours and let the happiness come to you on Relax Radio. Tune in to
Now, when children are learning mathematics, a good teacher will encourage them to spot patterns, because maths is all about patterns. There's so many patterns in mathematics, and to think why those patterns occur, and always to be able to understand and explain why things happen. So we've spotted a pattern for triangle numbers. We spotted that handshakes, the answer to handshakes, seems to be given by triangle numbers. So why? And now we're going to look at why. Because you see, if you look at that picture, and if you think about it, if you're listening to the radio and you're not seeing this picture, the picture has 2, 4, 6, 8 people standing around a circle. And we did this with string. We talked about doing this with string. It's what you call people maths. So when we talked about this a couple of weeks ago, we talked about 8 people around a circle, and each of them, passing a ball of string across the circle, not to the next person, passing a ball of string across the circle to everybody else. We did it in a continuous loop, but we won't go back over that because there was a lot in that. In fact, we also did a one on what was it, Caroline? Path to the Stars. So
I'm just looking for that picture, because we had a picture from Maka doing exactly that in real life,
exactly.
in that dome. And I'm looking for that
at the top.
picture.
Anyway, what you can do is to look at all of these activities: Path to the Stars, handshakes, and mystic roses, on the Aiming High website, and you'll see then the connections which we're talking about. We've only got 10 more minutes, so we need to move on. Now, in this picture, what you see is 8 people with all of the chords across the circle, which are lines that go from everybody's hand to the 7 other people. Okay? So what you see from each person there is 7 chords across the circle going to each of the other 7 people. So then 8 people each shake hands with 7 other people. Does that sound familiar? It's actually a picture which illustrates the idea of the handshakes. So in a sense, the maths is the same. It's what we call, what I often call being in disguise. You see, the handshakes was this mystic rose in disguise, and they were both triangle numbers in disguise. And there's the correct mathematical term is it's isomorphism, which means things change in the same way. So there's your connection, and isn't that lovely? And so this begins to give you an explanation of why it's triangle numbers. You see, if you think of 8 people, each shaking hands with everybody else, when there are 8 people in the room, each person shakes hands with 7 other people. So why isn't the answer 8 times 7, which is 56?
Why is the answer 8 times 7?
Why is it not 8 times 7?
Or why is it not 8 times 7? If you look at each, 1, 2, 3. Okay, what have we got there? 8. Well, each of the 8 people has 7 chords, 7 diagonals. That's what Sophia meant by the diagonals, 7 chords. But whilst some of them they don't all have 7.
No, they all have chords. 7.
They double up. Yeah, but they double up. So you've already counted 7 with the first person. So the second person along, you only have to count 6 of them. Oh, here we go. There goes the triangle.
No, wait a minute, Caroline.
No, the second person, you're only counting 6 of them.
No, if there's a line that goes from you to me, we're 2 of the 8 people in the room. If there's a line that goes from you to me, and I count that as a handshake between us. But I also have counted the line that goes from me to you. So I've counted every line twice.
Yeah, that's what I was saying. I clearly didn't say it very well.
Oh, you did? No. 8 times 7. And half of that because every line was counted twice. Now, if you look at this summary here, then, if there are 2 people, there's 1 handshake, which is the first triangle number, or we call T1 rather. And if there are 3 people, there are 3 handshakes, which we call the triangle number T2. If there are 4 people, there are 6 handshakes, which is the triangle number T3, and so on. And okay, so with as the pattern goes on, you can see for yourself there on the screen. With 6 people, you've got 1 plus 2 plus 3 plus 4 plus 5 plus 6. Or T15, and that's 15 handshakes, which is T5, and so on. And so that shows you why everything connects with everything else, which is a lovely idea. Now, there's only 8 people around that circle, and it's something that if you're a teacher, you could get your children to do as people maths with a ball of string. And if you wanted to do it on pencil and paper, then it's a very easy diagram to draw. And Caroline remarked when we last talked about this, that smaller children could draw that, and they could then colour in parts of it to show the symmetries and to make it look a pretty pattern.
I'm always looking for ways to include the younger children or the lower attainers, and this is such a great exercise. You start with a circle with only a few dots, or even just 2 dots, and it just gets the insight in how many lines do you need to join 2 dots. Well, it's only 1, even if they're on the circumference of the circle, and then you just add 1 more dot. Now how many lines do you need? Add 1 more dot. So start really simple, and then the child can stretch to the point at which they're then stretching, and then you stop for a moment, another day, and maybe
now, Caroline, I'm very conscious that we have actually we've taken longer than we had planned to talk about some of these things, and we do want to say about women in maths and science, don't we?
Oh, so go ahead. Oh my goodness, Thursday, yes.
So we've only got a short time to do that, and so we need to look again at the triangle numbers for T15 and T16, because you see these 2 mystic roses are slightly different, and it's intriguing that with 16, of course, you've got diameters in, so all the lines go through the center. We saw that last time we talked about it. And with an odd number of people around the edge, if you think of it as people around the edge or points around the edge of the circle, then none of the lines go through the center, and you've got this hole in the middle. But you see from what you that for 15, it's 105 handshakes, and for 16 people, it's 120 handshakes. Now then, what we want to do is to talk for our last 5 minutes about women in maths and science.
I had completely forgotten about this. Go, go, go. Yes. Wow.
So the reason is that the United Nations General Assembly adopted a resolution declaring that 11th of February would be the International Day of Women and Girls in Science. And so we've found this very nice website. Now, Caroline, do I have to stop sharing and share again?
Yes, you have to stop sharing. Well, no, we can see it, but it's quite small.
Oh,
no, I think it might.
No, we'll just talk through. Okay.
Can you press, Tony? Press the green button on top left. The maximum.
Oh, what a good idea,
one.
Caroline. Yes, that's better. Thank you.
That is much better. Yeah.
You can see it now, because you see,
yeah.
I can't see what other people are seeing, but it's on my own screen. Well, I can, but anyway, I wanted reassurance. So sorry about the adverts here, and we will give you the link to this, because we're not going to be able to do justice to this wonderful set of 20 women. Now, Mary Anning was a remarkable lady, This is on the coast of England, around the place called Lyme Regis. It's the Dorset coast, which is often called the Jurassic coast, because she found fossils there of dinosaurs, huge, huge fossils. And the scholars from the universities, well, that was Oxford, I think, university got interested, and they came down to Lyme Regis. And she was quite a simple woman who'd just been collecting seashells to sell in her father's shop when she found these fossils. And then she became actually just as skilled as the highly educated archaeologists. Amazing, isn't it? So,
Yes.
Caroline, do you want to talk about Maria Sibylla Merian?
So, no. You talk about
Well,
her,
she was
'cause
a botanist. Okay, she was a botanist, and she made discoveries like insects hatched from eggs. She was 17th century, so it's a long time ago. So a lot wasn't known then, and she studied insects, and she wrote, and she drew their pictures of them and classified them. So I'm going to move on quite fast because we haven't got much time. Then there's Sylvia Earle. She was a diver, much more recently, in 1935. And she did a lot of research about oceanography. And then this was the first, Mae Jameson, she was the first woman, went up in a space shuttle in the 1990s. Maria Gobert Mayer, she was a theoretical physicist. Now, I can't do justice to this in 5 minutes, but I do recommend you read it for yourself. I'm going to
just to let them know, Toni. If you on the AIMSEC Facebook and the YouTube, the Bubbly Maths YouTube, I will be putting this as a link that you can click. So
yes,
it's got to
absolutely.
come back in once
Now,
it's live, once it's settled, and I can't add it right now. I can only add it afterwards. I don't have that link.
I want to briefly say, I want to briefly say about Mariam, because she died a couple of years ago, which was absolutely tragic. You see, she was quite young when she died, but already in her lifetime, she'd won a Fields Medal, which is like the Nobel Prize. There isn't a Nobel Prize for mathematics. The equivalent is the Fields Medal. And there's just one more lady I want to mention, because she is so amazing. She's still alive, this lady.
Still alive. She's not just still alive, she's still working.
At the age of 103.
She was born in 1918, over 100 years ago, and she is still working. Now, that's it, my holy grail. She's my inspiration. Still working, still presenting, still out there giving presentations with a microphone at 100.
Well, she's directing some research that other people are doing.
Still presentations at 100.
And Caroline, it's particularly, I really wanted to mention her because it's all research into the human brain and memory and learning. And Caroline does an hour before this hour every week on a Monday, when she talks about the mindset. And the whole idea of the mindset is that the human brain has got some plasticity. It can learn a lot more and do a lot more than people ever believed possible. And this is recent research, really. It's these wonderful discoveries have been made. I mean, she was a groundbreaker in this field, and she's been working in the field for a long time. But a lot of big research was being done in Stanford University in California, and this Brenda, this woman, has been very, very influential, and worked with not just scientists, well, they're all scientists, of course, but doctors who've done surgery on the brain and discovered amazing things. So That's
So
all about the mindset.
We will. I'm just going to work out how to stop that, and we will put that link all over the place on the various places where this has gone live. If you send that to me, Toni. That is
Yes.
all the time we have for this week. Unless there's if you've got something else you want to say, Toni, before we finish.
No. I just want to say goodbye because we've said all we were going to say.
Thank you so much for joining us. Thank you, our team from Maca. That was absolutely splendid for us. We've had loads of people commenting and joining in. Joan, Almany Floss, thank you very much. Tanzila. We've had lots and lots of people joining us today. Thank you so much. And we'll see you next week at 5 o'clock UK time for the Happy Maths Hour. Thank you, with something else exciting and intriguing and mind stimulating. See you next week.